G'day guys, welcome back to my channel. I got a few interesting things I just want to point out before we go on and continue working on this panel meter. Sorry for the fact I'm holding the phone, I will place it in a holder in a minute. But the other day I was saying that I would try and power this up off of a battery instead of a power supply. And as you can see, there's nothing going on here. It's getting powered off of a battery. So I've hooked the scope up, as you can see, ground and the input of the regulator. And I'll take my battery I've hooked up the meter to the battery, as we can see. And look at the scope. So, like I said, the output of this power supply is extremely clean. Because initially I thought it might be the two regulators, the one I was powering it off here, the LM7812, and this regulator having a sort of a seesaw effect. But I could tell you it's not that. As soon as I plugged it into the output of my power supply, because that thing's really quiet, it's about 50 microvolts RMS of ripple and noise. So, you know, very quiet. Actually, just before I put the phone down, I'll just go over to my computer screen for a sec. Let's get out of this. When I was hunting around for a data sheet for the regulator, at first all I could find was this Asian sheet, and I could see a couple of specs like plus minus 3%. We don't know what that is, but anyway, 40 millivolts, 1.2 microamps, 50 parts per million per degree Celsius. So we know it's got a really low temp code. The other thing I found interesting is it says everywhere that it's a 24 volt CMOS part that takes 30 milliamps. I ended up finding a Holtec data sheet for the same part in English, and it also says it's a 24 volt part. And if we scroll down to the absolute maximum ratings, it says actually 28 volts. But these panel meters are being sold. I need this to focus. Come on. I don't know if you can. There you go, 3.5 to 30 volts. And you know, they're just literally they're relying on the 150 ohm resistor and quarter of a volt, half a volt max drop on the Schottky diode. It doesn't work like that. You can, if you have a shunt regulator, not a linear regulator, but a shunt regulator. I guess it's a form of a linear regulator. But anyway, a shunt regulator. If you have a shunt regulator, let me put this battery away and get some paper. So I can just make a quick little drawing that will make a bit more sense for you guys. So say you have your power rail here, your ground here, right? And you have your shunt regulator. Let's just say it's a TL431 where you connect the reference pin to the anode, and I always get anode and cathode mixed up for positive and negative. Anyway, you connect the reference pin to one side if you just want it to be a 2.5 volt reference, right? And it forms a shunt regulator. You also have to add a series resistance to it for it to drop the voltage across, because what it's doing is it's acting as a shunt, so sort of like a variable resistor. So if you put it directly across the rails, it would pop, it would go up in smoke. So you need to have a series resistor in there to drop most of the voltage across, or current, limit the current to it, so that you can drop the voltage without having too much current passing through it, hence being too much power and popping it. Anyway, I know I'm going on here, but with a shunt regulator, if this device, like a TL431, I think its maximum input voltage is 36 volts, I think, don't quote me on that, but I think it is. And say you've got 45 volts over here on your input, right? You can take a resistor, go into a capacitor. Now your resistor value has got to be fairly large enough in value, and your capacitor's got to be fairly large enough in value, so that when this 45 volts comes in, essentially the resistor limits the flow of power into the capacitor, which, as we all know, charges up like a battery. And the bigger the capacitor, the longer it takes to charge up too. So higher the value of the resistor, the longer it takes to charge up. Bigger value of the cap, the longer it takes to charge up. So you work out how much current you need to pass through the circuit continuously, and you determine your resistor value on that, and then you work out your capacitor value. And what happens then is when you turn the power on, these 2 points here coming off the capacitor, when you first turn the power on, they're at 0 volts, and it will ramp up slowly as the capacitor charges up to the 45 volts. But the thing is, your shunt regulator, whatever voltage it's set at, so 2.5 volts, 36, whatever, let's just say that we had a voltage divider on the shunt regulator, and we're actually feeding the reference pin into the voltage divider on the output, and we didn't have this here. Let's just say we had it set at 18 volts, right? What would happen is, as this capacitor is charging up, when you flick the power on and your 45 volts comes rushing in, the voltage on this capacitor starts going up to 45 volts. It doesn't happen instantly. And as it gets to 18 volts, somewhere around here, right, your shunt regulator turns on, pulling the voltage down and dropping it across the resistor and that resistor, and the voltage will never actually rise to the 45 volts on the capacitor. So yeah, you can usually do stuff like that with some parts, and only for small voltages. You can't, I wouldn't try and stick like 240 volts into a network like this on a TL431. I think that might be a bit too much, but yeah, the point I was getting at is you can sort of do stuff like that with a shunt regulator, where you've got a series resistor going into a capacitor and then going into your regulator device to sort of limit the input voltage on startup. But that's not what's going on here. This is literally a linear regulator, so the power goes in one pin and out the other, and it's tied to ground too. This has got a series pass transistor in it, and some, usually like a band gap voltage reference, and a constant current source, and an op amp, and some temperature stabilization stuff, and a series pass transistor, and that's all crammed into the one package. But yeah, you can't do that. You can't just go stick 30 volts in a 24 volt CMOS part. That's just ridiculous. So it's a good thing I'm running these meters off 12 volts. I'll say that. But anyways, as you guys have seen, the meter is oscillating on a battery supply or my power supply. So we've put it back on the power supply because there's no need to eliminate that. That's not what's causing the oscillation. So the next thing we're going to do is we're going to take our clip off the probe here. Excuse my workbench being so small. I need to, like I said, redo this lab and make everything bigger in here. Hang stuff up on the wall, fix the floor, make bigger workbench areas, but we're getting there. So what I'm going to do is I'm going to have a little probe around on here, particularly on the different capacitors and the power rails, this op amp and that. I want to see what waveforms I see. If I see anything that suggests this oscillation that we're seeing. I'm not seeing anything there, but that could be the ground side. Nothing there. Okay, just found something. Okay, we've got... I don't want to move the phone. That's the annoying thing about having the phone in a holder and then probing around. I'm ordering a phone stand that stands on the floor so I can sort of sit the phone behind me facing off on an angle so you can see what I'm working at, and the multimeter and scope screen and all that too. But for now, looking down, it's awkward because I want to show you guys the scope screen. But you know what? I'll do it for you. It's just a little bit more work for me. But probing on not the little surface mount capacitor there, but the one I've added. Having a look on its pin, we have this oscillation here. And if we come back to the output of the regulator, that's the exact same oscillation. So this oscillation, the frequency is all over the place, but it seems to be around about a kilohertz. Going back to the input of our regulator, sorry guys, there's a good spot. That really kind of does look a little similar to the waveform on the outside, but being chopped up, possibly with, I think some of the elements inside the regulator may be oscillating also, like the op amp that would be inside it, and then maybe the series pass elements having a bit of a diode effect on it and clipping it. Not too sure what's going on there, but it's definitely making its way out, whatever that is. It's causing a problem. So the other night when I changed things around on the board, I left this 10 microfarad multi-layer ceramic capacitor on the board. I never changed that to a better style of capacitor. I'm thinking what I'm going to do, I'm just going to quickly take these two wires off so they're out my way, and then I think I'll take off, I won't take it off straight away. What I'll do is I'll take these two wires off, and then I'll go get, we've got 100 microfarads at 25 volts, that'll do. We'll add this across the one that's there and then remeasure and see what happens. That could be a bit of a problem. I'm gonna have to put a capacitor there that's bigger than that one and turn it off by disconnecting from here before I disconnect from here, so that the LDO on power down doesn't have a high capacitance on its output to its input. because I think they can damage it. I'm not sure. Maybe it just does it to some devices and not others, but I don't want to fry it. So we'll take these wires off. These guys, I tell you, I never thought I'd spend days working on a freaking panel meter to get the accuracy close to right, and then find out that it's oscillating on top of it. Just never know these days what's going to happen. We're just tacking this on just for test purposes. You'd never in practice use legs this long, but we'll see if it has an effect or not at least. The thing is, if you're prototyping something, especially trying to rework a PCB that's already designed, you don't really want to go playing around with it too much, because the more you stick heat on it and move things around, the more you'll start to peel up traces and pads and burn things, and you know, it's not a piece of breadboard that you can just pull things in and out of. So we want to try and be as minimally invasive as we can. I've just got a capacitor for there. I'll just go get, say, a 470 micro out the drawer. Do a trick, 470 at 25. Alright. Plug this back in. That 100 microfarad capacitor may have just popped to that regulator. No, my wires are just popping out. It's a little bit of a trap for young players. You can't just go and put bigger and bigger capacitances, like within reason, on the rails of say a little regulator like that, because it might not have the output current to supply that peak current. When a capacitor is completely empty and it goes to charge itself up, when you supply voltage to it, it tries to pull in that charge instantly. It doesn't really charge up slowly like a battery. It almost happens instantaneously. So it wants to pull a lot of current very quickly, and that can be damaging for a small part like that. So anyways, I'm going to have a look at the input again. Okay, so that is very, very interesting. I'm going to show you guys. Bearing in mind the capacitor I've just added is on the output of the regulator. It's only filtering that little bit of ripple that we had on the micro. But that's what the input looks like now. Remember before it looked like that, but it had a whole load more high frequency pulses all over it, and it wasn't rounded out. So that's actually quite interesting. It appears that small oscillation coming from the micro is actually making the regulator oscillate. So really careful here. Yeah, so we want to power it down like that so that the main capacitor dies first. I know that didn't happen before when the wires were popping out the breadboard and I was trying to stick them back in. There is a chance that I will destroy one of these panel meters, but so be it. They're already crap and need fixing anyway. If I have to destroy one to work it out, so be it. Like I said, I'll try not to, but... So now what I'm thinking, the ground plane on this board, how good of a job did they actually do on it? quite curious. I'm wondering if there's a ground loop problem on this board, because it really looks... I already found a couple of things that weren't grounded to the right location. That's why I moved the leg of this capacitor here over to the common ground point down there, because it was tied where something else was tied to a ground point. It's sort of like having two star grounds on the one board. I think that's probably not the best way to explain it. Oh, you know what, I'll leave that solder there for now. I'll clean it all up and make it look pretty later. For now, if you're wondering why I was just discharging those capacitors, no, you shouldn't short out fully charged up caps, but one, they weren't fully charged, and two, they were small values, so they weren't going to dissipate a lot of power. You do that to a fully charged fair value cap, you can damage it. The reason I was discharging them is so I don't pick them up and go and put them in a circuit and inject voltage into it and pop something. You'd be surprised how often that's happened to me. So I want to have a look at these other 2 points here. This point here, it's labelled V, that's just the output from the regulator, and G is ground. But I want to have a look at these other two things and see what's on them. And then I'm going to look at the waveform on the inputs to from these resistive divider networks from the micro that goes to the display. I want to see what the multiplexing to the display is doing, because I've got a funny feeling, I mean obviously the thing that's going to be drawing the most current here will be the multiplexed display, and because it's multiplexing it, it's, I don't know if you guys see that in the camera, if the display looks sort of like wavy, but essentially what it's doing is it's not displaying all those digits at a time, it's scanning through very quickly and refreshing it digit by digit, so that we can effectively use the display with a lot less pins. So that's going to cause some pulsing and some current spikes. So I've got a funny feeling that's actually what is the source of the problem, but let's see. So on this pad here that's labelled R, there is a waveform on it. Looks similar to the 3.3 volt regulator output. I'm just comparing the two myself. Yeah, it's exactly the same. I wonder if those two pads are actually electrically the same pad. No, they are not. Is there like a high value resistance between them? Mega ohms. Okay, so just out of curiosity, is okay, so there's a couple of other pads here labelled R and S. And there's also a little spot on the board that says key. And it looks like you would put a button there. Maybe some sort of pot for adjustment. But no, that's a button. It's for a button. And the button does not go to these two pads either. There's some extra functionality on this board too that I don't know what it is. I don't know if that's like a programming header, if it's something to tweak it. to adjust it. I don't know what the button's for. It's quite interesting actually. I might actually solder the button on there and press it and see, or just get some tweet. Now let's do that now. Just out of curiosity, what does that button do? Absolutely nothing. I think it's like a reset. I think that's reset for the microcontroller. Bit odd. Alright, well, I think what I'm going to do, I'm going to up the input capacitor to something a lot bigger than 1 microfarad. And oh yeah, let's measure the display and see what's on the display for ripple. Yeah. Okay. I'm going to get the part number off of this display and see if there's any data sheet recommendations for driving this to help with current pulses. Like, I don't know. I'm just going to have a look at the data sheet and I'll come back. But basically what's going on here is this multiplex display. I'd say it's just basically taking 2 bigger current pulses and that's going back through the regulator causing an oscillation. So I'm just going to get the data sheet for this display and I'll be back, alright?